Okay, so now let's derive the mole balance for species J. So starting from this general form of the balance, let's write down what the mole balance is for this species. So the accumulation term, this is going to track how the number of moles of species J accumulates over time. So the way we write that is a derivative, dnj dt. And this is going to be equal to our in minus out plus net generation. So we're talking about flow rates, then we denote those with the letter F. So that's going to be equal to F of species J. And we're going to give this a subscript of 0. That's going to denote that this is our flow rate in. This is our in term. Minus F J. This is our out term. I'm not going to give it any other subscript. I'm just going to know that this is my outflow rate. And then plus my net generation term. So the units on all of these terms are what? What are the units? The units on all of these terms are moles per time. So the mole balance, all the terms are always written in units of moles per time. So the one term, everything here is fine except for our GJ term. So we have to think of a way to write this. This is non-descriptive. And in fact, what we're going to do is write this so that it's a function of a reaction rate. There are two different ways to write this term depending on what's happening with the system variables. So let's pause there and think about, when I say system variables, what system variables am I talking about in the study of chemical reaction engineering or chemical reactor design? So what system variables are relevant in a chemical reactor? So think of some. So some variables certainly that are important are concentration. Other variables of importance, temperature. You may be thinking pressure. Pressure, at least for a gas phase system, we're going to show or maybe recall that is proportional to concentration. Another variable of important catalytic activity. So basically, we're going to think about different variables in the system, and we're going to think about two cases. Number one, those variables are all uniform. If all the system variables are uniform, then the system is said to be well mixed. So if all of the system variables are uniform, then GJ, the net rate of generation, is going to be equal to the net rate of reaction times the system volume. So we'll say that's equal to RJ, the net rate of J, times the system volume. And we can say that since the system is well mixed, then the reaction rate is uniform over the entire volume. So we can just take the reaction rate and multiply that by the volume. So when we do that, what does that tell us about the units of RJ, the rate, the net rate of J? What units does that have? So if we scroll back up here, and we see that on the mole balance, the units are in moles per time. And here we have this net term must be in moles per time, and we have this volume term here that tells us that the rate must have units of moles per volume per time. So that's for the scenario where the system is well mixed. We have well mixed, we can write our generation term as the reaction rate times the volume. In the case where it's not well mixed, that means we have gradients going on. So we have a system volume, and in some places the rate might be equal to one thing, and in another place the rate might be equal to another thing. In that case, we basically have to scan over our entire volume and all of the different rates and basically add them all up. So I have a little volume here with one rate. I'm going to basically take that rate times that volume, another rate over here, another volume over here with another rate. I'm going to take that rate times that volume and basically sum them all up. Since they probably don't break up so discretely like that, what we probably have is it's needing to take an integral. So we would have Gj equals to the integral over the volume, Rj dv. So in this case, Rj is a function of volume, so we're going to integrate over the volume. That we're going to integrate the rate over the volume in order to get Gj. So this, in effect, is integrating over all of the rates and the volume. And in this case, Rj is a function of volume, whereas in the well mix case, Rj is uniform over the entire volume. So to be honest, we are never going to encounter this case in this class. We're always going to assume the well mixed case. So we're lucky in that regard. But just to think about some systems where we have gradients, since lots of systems have gradients. And I should say the reason that we're not considering the systems with gradients is because the well mixed case gives a pretty good approximation. So we aren't really losing too much in terms of the solution, but we are saving ourselves a lot of solution procedure. But just thinking, for a realistic system with gradients, what are some systems with gradients? So think that you encounter on an everyday basis or that you are aware of. So think of some. So some examples that students have given in the past are, of course, when you have non-perfect mixing in a reactor, or non-ideal behavior. Thinking of some, more familiar systems, some non-chemical reactor systems. One example that was given one year was Lake Hartwell. I think anyone who's swam around in a lake, you can actually feel temperature gradients in the water, particularly if the sun is really hot and it's early in the year, so the lake hasn't gotten too warm yet, but the sun will warm the top layer of the water, and then the deeper you go, the cooler it will be. Yeah.